Alright, so let's review the electron configuration and electron filling from the periodic table. In this lecture, we want to show you how you can write abbreviated electron configuration and also electron configuration of transition metals, and then we move on to electron configuration of ions. So remember that in the periodic table, the period number corresponds to the shell. So we have S block, P block, and D block elements in the periodic table. So here are the S block elements. So these are S block elements. Here we have the P block elements. And the transition metals are D block elements. So also we learned that group number for main group elements, the group number equals to the number of valence electrons. So we can look at the location of the elements in the periodic table, and by just looking at the location of the elements in the periodic table, we should be able to tell what the electron configuration of each element is. Now let's look at a couple of examples here. So let's say you want to write the electron configuration for, let's say, sodium. So to write the electron configuration of sodium, we look in the periodic table. Sodium is in period 3. So to get to sodium, everything before period 3 needs to be filled up. So 1s2, 2s2, and 2p6 are filled up. Now sodium is in period 3. Sodium is a S block element, and sodium is the first element of the S block elements. So this is the electron configuration of sodium. Now if we look at, for example, silicon, silicon is in period 3. So it means that period 1 and 2 orbitals are completely full. Now silicon is in period 3 and it's a P block element, meaning that S block are completely filled and P sublevel is being filled up. And silicon is the second element of the P block element. So this is going to be the electron configuration of silicon. Now, as the number of electrons increases, the electron configuration becomes very long. So we want to look into writing the abbreviated electron configuration. So let's look at the electron configuration of sodium. So 1s2, 2s2, 2p6, up to here, we're using 10 electrons. Look in the periodic table and tell me what element has 10 electrons in it.
Neon.
Neon. So very good. Up to here, this is basically the electron configuration of neon. Neon is a noble gas where all the orbitals are completely full. We don't have any empty orbital. So I could write the electron configuration of sodium in a different way. So I can adopt the electron configuration of neon and then 3s1. So this is called the abbreviated electron configuration for sodium. So for abbreviated electron configuration, you basically adopt the electron configuration of a noble gas. The electron configuration of a noble gas, when you adopt it, you have to write that in brackets. Now, same thing for silicon. Up to here, 10 electrons. This is the electron configuration of neon. So to write the abbreviated electron configuration for silicon, I could adopt the electron configuration of neon, and what's left is 3s2, 3p2. Now, this abbreviated electron configuration helps me look at the valence shells and valence electrons better too. So now if you look at the electron configuration of sodium, your valence shell is 3 and you have 1 valence electrons. Or for silicon, your valence shells are 3s and 3p and you have 4 valence electrons. So let's do another one. We want to write the abbreviated electron configuration for magnesium. So to write the abbreviated electron configuration, you first find your element on the periodic table, and then you want to adopt the electron configuration of a noble gas that comes right before your element. So the noble gas that comes before magnesium is neon. Now, magnesium is in period 3. Magnesium is a S block element, and magnesium is the second element of the S block elements. Let's write the electron configuration for sulfur. So to write the abbreviated electron configuration, you first find the noble gas that comes right before sulfur. That would be neon. Now sulfur is in a third period and sulfur is a P block element. So S is completely full and sulfur is the fourth element of the P block elements. So let's write the abbreviated electron configuration for calcium. So the noble gas that comes right before calcium is argon. Calcium is in period 4. It's a S block element and it's the second element of the S block elements. So let's look at the periodic table and electron filling one more time on the periodic table. So we already talked about the first 18 elements and everything, all the elements that included only S and P sublevels. But how about transition metals? How do we write the electron configuration for transition metals? So let's look at the periodic table and look at this diagram here. So as you see from period 4, that's when we start seeing the transition metals. That's when they start. Now, in period 4, after the 4s, basically after calcium, that's when we start seeing the first transition metal here. Now, for transition metals, it's the d orbital or the d sublevel that's being filled up. So all the transition metals, their electron configuration, it's the d orbital that's not completely full. It's the d orbital that's being filled up. So when you have transition metals, we expect your electron configuration to end with d because it's the d sublevel that's being filled up. Hence the reason all the transition metals, we call them d block elements. But here is the thing. The first d sublevel that we expect to see is the 3D. But if you look at the periodic table, the 3D sublevel doesn't show up until period 4. So in period 4, you have the 4s, and then right after the 4s, that's when we first see transition metals, d block elements, but those are the 3D. And after you're done with the 3D, you fill up all 10 orbitals. Then since you're in a fourth period, you're gonna start filling up the P sublevel. So for transition metals, this is the exception, that the D sublevel is always one energy level lower than the rest. So when we write the electron configuration for transition metals, or when we have to deal with transition metals, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and right after 4s2, look at the periodic table. 3d comes into the picture, and right after the 3d, we have the 4p6, and then we move on to 5s2, and then look, after the 5s, we have the 4d10, and after the 4d, you can see in the periodic table that we have the 5p6 and then 6s2. So the exceptions are here. And the reason this is happening is because of orbital mixing, because from the third energy level, we are too far away from the nucleus. So nucleus is not pulling the electrons all that tightly. So electrons have lots of freedom of movements. And, orbitals, remember, those are the space in which electrons can occupy. So since nucleus is not pulling those, the attraction of nucleus for those valence shells, valence electrons, is not too much, we get a little bit of orbital mixing. What that means is that the 3D sub-level falls lower in energy than the 4p. So since it falls lower in energy than the 4p, it's going to fill up first. And after the D sub-level fills up, then we get to the P sub-level. So memorize the order in which these orbitals are being filled up. Also try to make the connection with the periodic table. It's always easier to do the electron configuration of transition metals from the periodic table. Keep in mind that the first row of transition metals you see, those are the 3D, because the first energy level we expect to see a D sub-level is from the third energy level. Now let's look at a couple of examples here. So let's write the electron configuration for titanium. And let's just focus on abbreviated. We write always abbreviated unless we're asked to write the full electron configuration. So titanium is in period 4. To write the electron configuration for titanium, we find the noble gas that comes right before titanium, which is argon. Now titanium is in period 4, so 4s2 is completely full, and titanium is the second element of the 3D. So this is the electron configuration of titanium. Now let's write the electron configuration for nickel. So number of electrons for nickel is 28. Now we're going to use argon as a transition metal, and then nickel is in period 4, so 4s2, and then when you get to the 3D, that's 3d8. Now let's look at the electron configuration of, say, arsenic. Arsenic has 33 electrons. So I'm going to adopt the electron configuration of argon. Now to get to arsenic, 4s2 needs to be completely full. 3d needs to be completely full too. Arsenic is in period 4. It's a p block element, and it's the third element of the p block elements. So let's do electron configuration of indium. So for indium, we're going to adopt krypton. In order to get to indium, 5s2 needs to be completely full. 4d needs to be completely full. And then indium is the first element of the p block elements, 5p1. Now let's look at a couple of exceptions for electron configuration of transition metals. Let's look at the electron configuration of chromium first. Then we're going to look at the electron configuration of copper. So electron configuration of chromium, I'm going to adopt the electron configuration of argon, 4s2, and chromium is the fourth element of the d block elements. Now let's look at the box diagram for chromium here. So in the 4s, we have 2 electrons, and in the d sublevel, we have 4. So in chromium, the d sublevel is only 1 electron short of being a half-filled d sublevel. Keep in mind that completely full and half-filled sublevels have exceptional stability, meaning that their energy is very low. So what happens here in chromium is that in order to become more stable, 1 electron of the 4s is going to move to the 3d. So what happens here is that 4s is going to give one of its electron to the 3d, and by doing that, the 3d now have the half-filled electron configuration, which is very stable. So chromium doesn't actually exist in this electron configuration. So the electron configuration of chromium is always 4s1, 3d5. Now, this transfer of electron from the s to the d only takes place if your electron configuration ends up with s2d4. And only 1 electron can do that. More than 1 electron, this doesn't happen. Now, same thing happens with copper too. So the electron configuration of copper is argon 4s2, 3d9. So in copper also, we have the 4s, and we have 9 electrons in the 3d sublevel. So what happens is that in order to make this 3d completely full, 1 electron of the s is going to jump in the 3d, or is going to get transferred to the 3d. And when that happens, we're going to end up with completely full d orbital, which has an exceptional stability. So the electron configuration of copper is argon 4s1, 3d9. So for any electron configuration that ends with ns2, n-1d4, the electron configuration is going to change to ns1, and minus 1 d5. And for any electron configuration where the electron configuration is ns2 and minus 1 d9, it's going to be ns1 and minus 1 d10. So not all the elements do this. Only chromium, molybdenum, tungsten do this. And from here, only copper, silver, and gold will do it. Now let's look at electron configuration of ions. So let's say we want to write the electron configuration of sodium ion. So we would expect 10 electrons for sodium ion because sodium metal by itself has 11 electrons. Now, one positive charge, meaning that it has lost 1 electron, so you would expect 10 electrons for a sodium ion. So the electron configuration is 1s2, 2s2, 2p6. Let's say you want to write the electron configuration of an oxide ion. Oxide ion has 10 electrons, so the electron configuration is 1s2, 2s2, and 2p6. Now let's look at a few more cations and anions. So let's write the electron configuration for calcium ion. So calcium metal has 20 electrons. Calcium ion has 18 electrons, so the electron configuration could be electron configuration of neon. 3s2, 3p6. And we can also write, let's say, the electron configuration of bromide ion. Which is going to be argon, four s2, 3d10, 4p6. The electron configuration of a sulfide ion is going to be neon, 3s2, 3p6. So for main group elements, you can look at the charge of your ion, and based on the charge, you either add or subtract electrons, and you write the electron configuration of the ion. Now let's learn another term here. So sodium ion has a total of 10 electrons. Oxide ion also has 10 electrons. So sodium ion and oxide ion, both of them, they have 10 electrons. So we say that sodium ion and oxide ion are isoelectronic. Isoelectronic means same number of electrons. So for example here, calcium ion has 18 electrons. Sulfide ion also has 18 electrons. So I can say calcium ion and sulfide ion. So 18 electrons, even argon, and argon are isoelectronic. Isoelectronic meaning that they have the same number of electrons. So let's look at the electron configuration of ions of transition metals. So titanium is argon, 4s2, 3d2. Now for transition metals, you always lose electrons first from the s orbital. So s orbital fills up first, and the electrons are going to be lost from the s orbital first too. So to write the electron configuration of titanium ion, titanium plus 1, the electron configuration is going to be argon, 4s1, 3d2. So for ions of transition metals, remove electrons from s orbital first, and then remove from d orbital. So in order to write the correct electron configuration of transition metals, it's very important to write the electron configuration of the metal, neutral metal first, and then remove the electrons. What do I mean? Let's say you want to write the electron configuration of, let's say, titanium 3+, titanium 3. So based on the electron configuration, so to remove 3 electrons, you move 2 from the 4s and move 1 from the 3d. So this is going to be the electron configuration of titanium 3. So I did this based on the electron configuration of metallic titanium. But let's say you don't do this. You just count the electrons. You say, okay, titanium metal has 22 electrons, and titanium positive 3 should have 19 electrons. And now you write the electron configuration for 19 electrons. That's going to be argon 4s1, which is completely wrong. So to write the electron configuration for transition metal ions, you first start with the neutral metal, just in the metallic form, and then you start removing the electrons. So let's do another example. You want to write the electron configuration for nickel 2. So to write the electron configuration for nickel 2, we are first going to write the electron configuration of nickel in a metallic form by itself. So nickel has 28 electrons. The electron configuration is argon 4s2, 3d8. Now for nickel 2, we're going to remove the electron first from the 4s. So the electron configuration of nickel 2 is argon 3d8. Now let's look at, for example, copper. That was one of our exceptions. We want to write the electronic configuration of copper 1. So to write the electronic configuration of copper 1, first I'm going to write the electronic configuration of copper metal, which is argon 4s2, 3d9, and I know that this is not correct, so the correct electron configuration is argon 4s1, 3d10. Now the electron configuration of copper 1 is argon 3d10. Now we can also write the electron configuration of copper 2, which is going to be argon 3d9. Now let's look at one application of electron configuration and box diagrams. So let's look at the electron configuration of, for example, titanium and titanium 1 and titanium 3+. So electron configuration of titanium is argon 4s2, 3d2. Titanium plus 1 is argon 4s1, 3d2. And titanium 3+ is argon 3d1. I'm also going to draw the box diagram only for these orbitals here, not all of them, just for the valence. So for titanium, this is the box diagram. For titanium plus 1, this is the box diagram, and for titanium 3+, this is the box diagram. So based on the electron configuration and box diagram, we can get some information about magnetic properties of the elements and ions. So anything that's paramagnetic it means that it has magnetic properties. And diamagnetic elements or ions, they don't have any magnetic properties. Now, this is a general classification of magnetic materials. Now, within paramagnetic, we have different types of magnetic properties. But if something is paramagnetic, for example, you can use a magnet on it. It's going to get attracted by a magnet. But diamagnetics, they won't. Now, how can we tell if something is paramagnetic or diamagnetic? So you can look at the box diagram and electron configuration. So any element or ion that has unpaired electrons So any element or ion that has unpaired electron in the box diagram is going to be paramagnetic. Any element or ion that has no unpaired electron is going to be diamagnetic. So for example, for titanium, titanium 1 and titanium 3, they're all paramagnetic. Look at titanium. Titanium has 2 unpaired electrons in the 3D. So this is paramagnetic. Titanium 1 is also paramagnetic. Because it has unpaired electrons. Titanium 3 is also paramagnetic because it has unpaired electrons in it. Let's look at the electron configuration of molybdenum. Molybdenum 1 and molybdenum 5. So molybdenum is one of the exceptions. The electron configuration is krypton. Five S1, 4D5. So molybdenum 1 is going to be krypton 4D5, and molybdenum 5 is going to be krypton 4D1. Now let's look at the box diagram to look at the magnetic properties of molybdenum and molybdenum ions. So for molybdenum, we have one electron in the 5s, and 5 in the 4d. So molybdenum 1 we have 5 electrons in the 4d, and for molybdenum 5 we have only 1 electron in the 4d. Now to see if molybdenum and molybdenum ions are paramagnetic or diamagnetic, we look at the box diagram. So for molybdenum, I see a ton of unpaired electrons. So molybdenum is paramagnetic. Molybdenum 1, I also see unpaired electrons in the box diagram. So this is also paramagnetic. And molybdenum 5 is also paramagnetic because it has unpaired electrons.